So we have learned about the properties, inverse Laplace transformation, how to do union bilateral Laplace transformation, and now we are on the last part of Laplace transformation. We will do an application part. So right now, first of all, we are going to understand how to solve differential equation. Laplace transformation is the ultimate machine to solve any differential equations, but in signals and systems, we face a linear constant coefficient differential equation most. So, we are going to use Laplace transform to solve linear constant coefficient differential equation right now. Alright, so here is the first example which I have chosen. It's a straightforward explicit differential equation with an initial condition, because one initial condition because of first order equation it is, and we want to solve the differential equation. So the first process to solve this differential equation is to guess a solution. We want is to guess a Laplace transformation. We want to guess that the Laplace transformation of y of t is y of s. Then what's the Laplace transformation of y derivative of t? It's going to be s y of s minus y of 0, or as y of 0 is given, it's going to be s y of s minus 1. Alright. And what's the Laplace transformation of the right hand side ut? It's going to be 1 by s. So now, since we know the Laplace transformation of all the terms, we can take the whole equation in the Laplace domain. So taking in Laplace domain, what do we get? If we substitute for y dash, we will get s y of s minus 1 plus 2 y of s is equals to 1 by s. So if we take y of s common, it's going to be s plus 2 1 by s plus 1. So in other words, it's going to be s1 plus s1 plus s, and then if we take this factor on the right hand side, is going to be s plus 1 divided by s plus 2. Right now, if we do inverse Laplace transformation, we can come to yt. What's the technique to do inverse Laplace transformation? Partial fraction. All right, so how are we going to do partial fractions? Two first order factors, non-repeated factors, very easy. We're going to use a shortcut. So firstly, one discrete term for s and one discrete term for s plus 2. What's the pole on s? The pole is 0, so all the rest other places of s you put 0. So it's going to become 2 and 1. And what's the pole on minus s plus 2? The pole is minus 2, so all the other places of s you put minus 2. So it's going to be minus 2 and minus 1, so minus minus gets cancelled out. So that's how 1 by 2s plus 1 by 2 1 by s plus 2. Right now we can do inverse Laplace transformation, and it is going to be 1 by 2. The inverse Laplace of 1 by s is u of t, and inverse Laplace transformation of 1 by s plus 2 is u of t e to the power minus 2t. Alright, so you can understand the hierarchy first of all, that you're going to guess some Laplace transformation, and then all the derivatives, first order derivatives, second order derivatives, or integrals in a differential equation, though there shouldn't be any integral, if there is, are going to become some algebraic operations in the s domain, and then you will have to solve for ys, and after you solve for ys, you need to do inverse Laplace transformation. Alright. Now we're going to solve a circuit. Alright, many times the differential equation is not explicitly given. In circuit, your first task should be to build the differential equation. Alright, so if you use KVL, it's going to be minus x plus twice alpha I plus alpha di by dt plus y is equals to 0. Now I is equals to, we know, c dy by dt, or c is simply 1 by alpha dy by dt, right? I, for capacitor, the IV characteristics is I equals to c dv by dt, and here the voltage is expressed as y. So if we substitute for the y value, then we will get, for the I value, d by dt 1 by alpha dy by dt plus y and x of t. Alright, then alpha gets cancelled out, 2 dy by dt plus alpha 1 by alpha would get cancelled out, d square y by dt square plus y is equals to x of t. Alright, then again we need to propose a Laplace transformation for y of t is going to be y of s, and in the circuit it is given that, suppose it is given that all initial condition is 0. If all initial condition is 0, then we know the Laplace transformation of y dash of t, that means first order derivative is going to be s y of s, and the second order derivative is going to be s square y of s. And what's the Laplace transformation of x of t? X of t is ut simply, so the Laplace transformation of ut is 1 by s. So if we take the whole equation in Laplace domain, is going to be 2s ys plus s square ys plus ys equals to 1 by s. So y by ys equals to 1 by s square plus 2s plus 1, which can be written as s plus 1 whole square. So right now we need to again do partial fraction, and as it is first order factor but repeated, so we need to propose a partial fraction. So according to our outbound rule, we are going to build up the repeated root slowly, repeated factor. Alright, so firstly for first term, first order, then second to the power of second, and as the factor is of degree 1, so the numerator is going to be of degree 0. Alright. So the next task, as I have discussed before, is to divide the whole side by the denominator of our partial fraction. So multiply the whole side by the denominator of a partial fraction, so that's going to become plus 1 square plus bs plus 1 s plus cs. So now you need to put some critical values to find out some of the values. So firstly, if you put s equals to 0, then b and c term gets cancelled out, so a dot 1 equals to 1, so a equals to 1. Secondly, if you put s equals to minus 1, then a and b term gets cancelled out, so c minus 1 equals to 1, or in other words, c equals to minus 1. Now to find out the value of b, we need to equate some terms. Now if we equate s square terms, there is a s square here and b s square here, so a plus b are the only s square terms, coefficients of s square terms, and in left hand side there is no coefficient of s square terms, it's 0. So b is also going to be minus 1. So if we replace the values of a, b and c, if we substitute the values, then we are going to see 1 by s minus 1 by s plus 1 minus 1 by s plus 1 square. So right now we can do inverse Laplace transformation. 1 by s inverse Laplace transformation is ut, 1 by s plus 1 is inverse Laplace transformation is e to the power minus t u of t, and this is simply the derivative. This whole thing is the derivative of 1 by s plus 1, so its inverse Laplace transformation is going to be e to the power minus t ut, and then minus 1 to the power 1 t to the power 1. So minus 1 to the power 1 is minus 1 simply, and a t. So this is our solution for this circuit. So you see, it's very easy. You need to propose an Laplace transformation, then you need to go on, move on, so find the equation for y of s, and then you do inverse Laplace transformation to come back to time domain. Thank you.